Okay. Yeah, so what I'm going to tell you guys about today is a project that I'm kind of working on, and some pieces of it are finished and some pieces of it are still in progress. But it's kind of, I've been trying to cook up a general way to think about questions of stability and semi-stability in moduli problems. And so let me just kind of frame the problem for you, like the general problem that happens in algebraic geometry a lot of times. So okay, so for us today, a moduli problem, let's just say it's kind of a functor from schemes to groupoids or sets. I mean, really, I'm thinking of it as a pre-sheaf in groupoids, but you can just think of it taking isomorphism classes as a functor in sets. So, and the goal of like a moduli problem is to come up with a scheme such that, so you have some functor, and the goal is to find maybe a scheme. This is the kind of horribly naive goal would be to find a scheme such that f of t is just equal to the maps from t into that scheme M. Okay, but this is, as we know, this is kind of this never happens. So let me give you some examples. So one example might be kind of the moduli of all families of varieties. So let's say flat families of projective varieties. So f of t is the group weight of flat families x over t, maybe possibly plus an ample bundle. And the appropriate notion of isomorphism. Another example would be kind of the moduli of, so f of t is parameterized isomorphism classes of vector bundles on x times t. And then, you have, this is a groupoid regarded with the appropriate notion of isomorphism. Kind of another example, a slight generalization of this is you could say families of coherent sheaves on x times t, which are flat over t. Or kind of more generally, there's a notion, so given a t structure, oh, here x was a projective variety, although the example that we'll consider most is when x is a curve, a smooth curve. So given a t structure on dbco of x, there is a functor which, f of t parameterizes flat families of objects in db co of x heart over t. So this is a kind of a, the notion of a family of objects in the heart of a t structure is due to Bridgeland. It just says should just be an object in the derived category of this x times t, whose derived restriction to every fiber should lie in the heart. And if you think about it, that's exactly what the notion of a flat family is for coherent sheaves on, a flat family of coherent sheaves on x would just be an object in the heart of the t structure in x times t, whose derived restriction to every fiber over t is also a coherent sheaf. I don't know. Let's say x is smooth, so it doesn't matter. Okay. Or no, it would still matter, yeah. But then you, yeah, right. Yeah, perfect, yeah. Well, yeah. No. Did the cohomology group say? I don't think so. No, no. Yeah, you can have a, I mean, yeah. I mean, the point is that you don't think about cohomology sheaves in the usual T structure. If you have a different kind of T structure, so you know, there are ways to get other kind of T structures on DB-Co that are more pedestrian, and you can you know, so the cohomology with respect to that other T structure is going to be, of the derived restriction to every fiber, is all going to be concentrated in H0. Like it should sit in the heart. The derived restriction to every fiber should sit in the heart. Yeah. Is that? So if you have a flat, yeah. Okay. Yeah. Yeah. So that's the notion. Okay. So then actually the most concrete example would be this thing, which is a G bundle. F of T is a G bundle. On T. So G is some kind of, let's say, reductive group. So G bundles on T along with a G equivariant map from P to X, where X is some variety that has a G action, and this is something, you know, this F in this example is what people refer to as the quotient stack. So this is some kind of souped up version of talking about kind of an orbit space of this sort of thing. That's an algebraic stack. Okay, so this is just, you know, so basically if you kind of if you're kind of already familiar with the theory of algebraic stacks, then this is all not, you know, this is all very familiar. And if you're not, then you can just think of any of these examples for the duration of the talk that I'm about to give. And I'll be kind of bouncing it back and forth between different examples of this kind. Okay, so just to review, so the things that can go wrong. So, you know, this functor f of t, so f can be non-separated. It can be, you know, well, just lots of different things can go wrong. The functor could be non-separated. You could have, you know, as a groupoid, you could have points that have automorphisms, but, you know, you could also f could also not be a finite, could fail to be a finite type. In any kind of reasonable sense. So in the example, so an example of this would be kind of, let's take the moduli of vector bundles over a smooth curve. You can consider things like this. So you can just fix an ample bundle on your smooth curve and let the power of D get higher and higher and higher. And there's no kind of finite type scheme that will be able to parameterize. You know, there's no. So there exists no finite type T with a family with a vector bundle on T times C hitting each of these, so hitting each isomorphism class. So there's no kind of there's no algebraic, there's no possible way to get a nice bounded algebraic family that kind of hits all the isomorphism classes, even though in this example I fixed the rank, I fixed the topological invariance of this vector bundle in the curve. I fixed the rank and degree. So this is kind of a, this is just kind of evidence that this thing is not like, a nice variety or a nice projective variety that we'd want to be studying. Okay, so kind of the goal when you actually try to, study when you actually, fix a problem that you're interested in, try to study it, would be the following. The goal would be to define, the goal would be to throw away some points in the moduli problem. So, which is identifying, a functor of semistable objects, which would be a subfunctor of your original moduli problem. And hopefully, F semistable has a good moduli space or coarse moduli space. And then also you might hope that the pieces that you've thrown away, you can actually kind of describe what the structure is. So the idea would be, the other goal would be to find a stratification of the unstable locus. So, and this is the thing that I'm going to focus on. So the idea would be, let's take the moduli of bundles on a curve. This is kind of a giant thing. We have an example showing that there's no way to kind of hit all the isomorphism classes with a nice finite type, bounded family. But kind of the moduli stack of all vector bundles on a fixed smooth curve is not a scary thing. And the reason why it's not scary is because it has so much structure on it. So in particular, there's some big open substack, which is the semistable locus, which has in certain cases has like a nice smooth projective coarse moduli space. And then in addition, beyond that, this moduli stack has a locally closed stratification by substacks with a very specific and clean modular interpretation that helps people kind of not be afraid of this whole giant moduli problem. So in other words, what we have, okay, I'm going to switch to maybe using X for stacks because I think of these as geometric objects. So in these cases, what you have is a stratification. So you have an open substack, which is a semistable locus, union maybe S naught, and so yeah. And so in the case of bundles, you'll get more and more and more strata because this thing is not finite type. But still, there's some nice way to kind of decompose the entire moduli problem like this. So this is the goal that, there are a few examples where this is kind of understood, like the moduli vector bundles on a curve being one of them. And then the goal would be to come up with a language where you could maybe extend this story to many other moduli problems that you'd be interested in. So basically the reasons why I'm interested in stratifications of this kind, one reason is to try to just literally just understand this moduli problem in as much detail as possible. The other reason, another motivation, would be kind of these, well, I guess in my 15-minute talk, I talked a little bit about ways of decomposing, ways of trying to compute the cohomology ring here based on knowing the cohomology ring of the stack and various correction terms. So there's a whole story there. There's also kind of there's a categorified version of that where you understand the derived category of the stack in terms of the derived category of the semistable locus and different pieces. So there's a whole story like that. Today I'm just going to talk about one kind of thing, which is like a virtual localization theorem. So let's say we're in the case of X mod G. So this was the last example I talked about above, and in this case you have kind of So in this case you might want to compute the holomorphic Euler characteristic. So if I take an equivariant coherent sheaf, I can look at the G invariant Euler characteristic. So the alternating sum of the G invariant sheaf cohomologies, and this has a decomposition. This has an expression like this. So there's a comparison formula comparing the G-invariant Euler characteristic of an equivariant coherent sheaf or an equivariant vector bundle with the same over the restriction to the semi-stable locus, and then you get some plus some correction terms. So let me just think about the case when G is just GM and X is smooth. In that case, the stratification here, so if G is GM and X is smooth, the stratification is just the BB stratification. Well, I mean, yeah, it won't be exhaustive necessarily. Yeah. Yeah. Right. Oh, yeah. Well. Yeah. You want X to be smooth and projective over affine. Yeah. You'll need that so that the strata are kind of ordered in a reasonable way. This is like where you just consider, the connected components of the fixed locus of this X, and then for each of those connected components, you consider the points that are attracted to that as the limit as t goes to 0, and that'll be when your X is kind of smooth, when your X is smooth and projective over affine, that'll actually be a stratification by locally closed subvarieties. Bialynitsky-Brula, yeah. Yeah, what? Okay. Yeah. Well, in that case, anyway, in this case, the correction terms have kind of a specific, I'll write down the correction terms for you. In this case, the correction term looks like the restriction to the ith stratum tensor something, which is sim of the normal bundle of the stratum inside X, tensor the determinant of the normal bundle. Ugh, this is a mess. Well, you can't help what nature gives you. So in this case, the correction term looks like this, and so, if there's always a local cohomology sequence relating if I remove imagine removing these subvarieties one at a time, and there's always a local cohomology short exact or long exact sequence comparing the invariant cohomology in the semi-stable locus and some kind of correction, which is the cohomology with supports along the strata that I'm removing. But the kind of miraculous thing, usually the cohomology with supports is not kind of a finite dimensional correction term. Usually the cohomology with supports is some big quasi-coherent sheaf. But in this case, the way the BB stratification is constructed, it's constructed exactly so that the normal bundle of each of the strata has negative weights with respect to the GM action that's contracting. So if you look at this correction, so even though this is like, this correction term is quasi-coherent, in fact, and the stratum itself is going to be kind of affine over the fixed locus, so it'll also be kind of equivalent to an algebra with negative weights with respect to the GM action. So in fact, even though this is a quasi-coherent correction term, only finitely many of those symmetric powers will ever contribute to the invariant piece of the integral. Yeah. The SIs are the strata. So the SIs are like the locally closed subvarieties that are being attracted to the fixed locus, which I haven't named. The fixed locus is the ZI. Yeah. So, yeah. I haven't really named it, but the SI is, this is my SI. And maybe this you can call the zi, or the connected components of the fixed locus. Oh, X semistable would be the complement of all the strata. So if this thing weren't projective, then they don't have to be, they don't have to fill it. Yeah. 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 Yeah, it should be, because the alpha is, those are just the functions, right? Yeah, that's true. Yeah, yeah. But there are other ways. This is just kind of an example of how of what the stratification looks like in this case. You know, this is, you can consider the BB stratification. You could also choose like a different, you know, ordering. So for some of the connected components, you choose the ascending manifold, and for other connected components, you choose the descending manifold. And in a way, GIT is exactly the thing that organizes those choices, so that you have a nice ordering of the strata, so that, you know, each one is closed in the complement of the ones above it. Well, so there are two ways to stratify that. One would be to have the, you know, depending on which GM I can choose a standard one parameter subgroup or the negative one parameter subgroup. And in one case, the stratum is just the origin. And when you remove that, you get projective space. Because if you choose the negative GM action, no points are attracted to, no points are attracted to the origin except the origin itself. And then if you choose the other linearization, the entire thing is unstable. X semistable is empty, and the entire thing is just a single stratum. Yeah, yeah. No, I mean, I think some of the normal bundle will still have a. There, it's kind of it's kind of a tautology, right? If the normal bundle is trivial, like there is no correction term. Right. So that in that case, you get that the. So there is no correction term, meaning it's just the identity. Yeah. This correction is just the trivial line bundle. Yeah.
Oh, it's sim star, sim zero.
Right. Yeah. Anyway, okay, wow. All right, so the reason, the story that I'm about to tell you, the reason why I got into it is because I was interested in extending this kind of localization theorem beyond the smooth case. And so it turns out that when your variety was singular, kind of the natural correction term that you can write down here, the kind of intrinsic correction term that you get, doesn't have this nice property that it has strictly negative weights with respect to the GM action. So this whole, the whole principle kind of fails. Essentially, the correction term, starts to pick up pieces of the cotangent complex of the stratum inside the relative cotangent complex of the stratum inside X, and it will just no longer have negative weights. So, in order to find a fix for this, I found that the right way to do this was to cook up a modular interpretation of the stratification, which is kind of what I'm about to tell you about. So, yeah. Yeah. So it turns out if you put the appropriate modular interpretation on the stratification, then it will come equipped with the structure of a derived algebraic stack, and for this derived algebraic stack, whose underlying classical stack is just the usual stratum, but you can think of it like a little derived thickening of that stratum. For that structure coming from this modular interpretation, the relative cotangent complex will still have negative weights, and so this you'll still be able to write down a formula like this. So that was like the thing that led me on this kind of crazy adventure. Okay, but let's kind of try to move along. So okay, so. So kind of it's a theorem. So let me say that the Hilbert-Mumford criterion. So let me go back. So we're in the case where X is, let's say, projective over affine, and there's a G action on it, and L is a G ample line bundle. So we're in the setting of GIT. Then the Hilbert-Mumford criterion says that a point lies in the semi-stable locus if and only if the following happens for all one-parameter subgroups such that there's a limit as t goes to 0. The weight of this G linearized ample bundle at the point, the weight with respect to lambda at the point P naught is, there's a convention here. What? Either way, yeah. I think I want it to always be, well, it doesn't matter. Okay, let me say if and only if it's always positive. So this is the Hilbert-Mumford criterion. But then there's a theorem of Kemp which says that Kemp says that if P is unstable, then there's a canonical map from A1 mod GM. Oh, whoops, sorry, I got ahead of myself. Then there's a canonical one-parameter subgroup. And it's canonical in the sense that it maximizes a numerical invariant. Well, you can't really so it's kind of not really a well-posed problem to maximize just the weight of this line bundle, because I can always raise my one-parameter subgroup to a power. But if I normalize by some norm of that one-parameter subgroup, then it's a well-posed problem. And in fact, if you try to find, there's a well-posed problem to find the lambda which maximizes, and there's kind of essentially a unique one. That's the theorem of Kemp. Kind of at the same time, so the reinterpretation of this so this is a canonical map from A1 mod GM into X mod G, maximizing a certain numerical invariant. So that you can think of, the data of a map from A1 mod GM into X mod G is just exactly the data of a one-parameter subgroup, such that the limit as t goes to 0 of lambda of t dot p exists. You can actually make, yeah. So that's a way to. Okay. So my claim is just that you can see the existence of Halpern-Leistner stratifications in the same way. So a theorem of Halpern-Leistner essentially says that so for any unstable bundle, so C is a smooth curve, so there exists a canonical filtration so I'll write it as a descending filtration. And I'll also do the following. I'll label these things with weights, which are just going to be integers. So So there's actually a canonical filtration along with a canonical labeling by integers, which maximizes so okay, so the notation here is to say that given a filtration along with a choice of weights like this, you can form this numerical invariant mu, and there's a, I mean, this isn't, so the existence of this Halpern-Leistner, this canonical filtration actually doesn't usually refer to the existence of these weights, but you can also kind of canonically put in these weights subject to the request that you're trying to maximize this numerical invariant. So right. And this E1 through EP is just the Halpern-Leistner filtration of an unstable bundle. But there is another way to look at this sort of thing. So another way to look at this canonical stratification is also, so there's a Riesz construction, so-called Riesz construction, which kind of will translate between the problem of vector bundles on C times A1 modulo GM. So GM equivariant vector bundles on C times A1, the category of such things is kind of well, essentially equivalent to the category of filtered vector bundles. So really what this is saying, what this theorem is saying, is that given an unstable bundle, there's this kind of canonical filtration on it, which amounts to saying that there's a canonical vector bundle on C times A1, which is equivariant with respect to the GM action. And this thing here is essentially the same as maps from A1 mod GM into bundles, into let's say, I've been a little bit sloppy with the if I'm working with SLN bundles versus GLN bundles, but I've been implicitly working with SLN bundles. So with trivialized determinant into bun SLN of the curve C. So there's this moduli stack which parameterizes families of SLN bundles on a curve, so families of vector bundles with a trivialized determinant. And if you unwind what it means to have a map from stacks from A1 mod GM into this moduli problem, that's exactly the same thing as having an GM equivariant SLN bundle on C times A1. So if you can kind of, chasing through these equivalences, what you find is that the Halpern-Leistner theorem, the existence of this canonical thing, says that for an unstable bundle, there exists a canonical map from A1 mod GM. So it's a map from A1 mod GM to this thing such that the point f of 1 is isomorphic to the, to the original bundle that you're looking at. So, once you think about it this way, like there's a kind of a natural generalization that takes shape. So both in the setting of geometric invariant theory and in the setting of vector bundles in a curve, you're posing the following question. So I take a point in my stack and I look at all maps from A1 mod GM, such that the point 1 is isomorphic to the given point that I'm exploring. And then to every such map, I should come up with a way of associating a number, just some real number. So in this case, it was the normalized Hilbert-Mumford numerical invariant. In the case of bundles over a curve, it's this gadget that I've written for you here. And then the question is, so a point you should call is unstable if you can find something such that this number is positive. And then if a point is unstable, you can now pose the question, is there a canonical map from A1 mod GM to your stack along with an isomorphism of the image of 1 with the point you're studying? Is there a canonical such map that maximizes this numerical invariant? So a general way to talk about a numerical invariant so I have to give you such a, in order for this outline of how you talk about instability in an arbitrary moduli problem to be complete, I have to tell you how to cook up a number. So here, for a map from A1 mod GM, in this case, it corresponds to a filtered vector bundle along with the choice of weights like this. And I've told you this is the number I want you to try to maximize. And in the case of a a GIT situation, I've given you this number. And so my claim is that they're both versions of the same thing, which is that I specify a cohomology class in H2 of the stack and another cohomology class in H4 of the stack. And then what? X is, so in this example, X was this is X. So and in this example, this is X. So right. So well, let me just, so to any such map from A1 mod GM, right? If I look at the pullback here of L, this lives in H2 of A1 mod GM. And now A1 mod GM deformation retracts onto BGM. So H2 is actually will just be isomorphic to, let's do everything with real coefficients, just so. I mean, really, I think, yeah, should be fine with rational coefficients. But so H2 of A1 mod GM is just isomorphic to R times a single generator in degree 2. And this is like the Turing class of the tautological line bundle in BGM. If I pull back a class in H4, well, H4 of A1 mod GM turns out to also be equal to isomorphic to R. It's one-dimensional, and it's generated by this Turing class squared. Yeah? Oh, squared, yeah. So in particular, I can define, to any such map, I can define mu of f to just be equal to f star of L divided by the square root of f star of B. And this is actually just a real number. So in the case of a quotient stack, yeah, in the case of a quotient stack, my claim is that what this numerator here is it's the pullback. So example is for x mod g, L is equal to the C1 of the ample line bundle that I've chosen. And that number, that weight of the line bundle to fiber of the point, under this identification, is just the pullback of that first Turing class. And the B in this case, well, so the B is pulled back from H4 of BG, because x mod g mapped to BG. And so it's pulled back from H4 of BG, and it's an invariant inner product on the cocharacter lattice. So a Weil group invariant on the cocharacter lattice. So, I mean, don't worry about the, if you're not familiar with this kind of group cohomology stuff, don't worry about it. Just that normalization factor that I use in the denominator there, actually you can think of that as coming from the data of a class in H4 of BG, or equivalently for H4 of the stack. And then, yeah.
So you can we just make also the semi-stability condition of this kind of map from GM.
Yeah. You're asking me to do that?
Yeah.
No, yeah. So the semi-stability condition says that, so for all P and X, so P lies in X semi-stable if and only if the supremum overall maps from A1 mod GM to X with an isomorphism f of 1 being isomorphic to P, if the supremum of, let's say, f star of L, let's just say if the supremum of f star of L is bigger than 0, let's say, or yeah. So I guess in my case, with the sign convention I chose over there, it should be negative C1 of L, something like that. So a point is semi-stable if and only if you consider all maps from A1 mod GM, and you can find one which makes this number positive. And then if this number is positive somewhere, then you should actually just kind of try to consider the normalized invariant. The fact that this is well defined depends on the choice of class in H4. So you should really only be choosing maps from A1 mod GM such that the map on the stabilizer group has finite kernel. So non-degenerate maps from A1 mod GM into the stack. Yes. There's a choice. Yeah, there's a choice. Yeah. Yeah. It depends on choices. Yeah, the semi-stable locus depends on the choice. So if you think about this, the semi-stable locus only depend on the class L, because it's defined. You can find a map from A1 mod GM such that the numerator is positive, and the numerator only depends on the class L. So the notion of semi-stability only actually depends on the line bundle. But if you want to find all this extra, if you want to discover all this extra structure in your moduli problem, you need a normalization. So you can kind of ask this question. Oh yeah, so right. So in this case, so for our purposes, what it is it's sufficient to, there are different kinds of ways you can talk about the cohomology of a stack, be it algebraic or not. But for our purposes, let's just say that a cohomology class will be just kind of the cohomology class of X will just, let's just say it's the limit over all maps from T to X of the cohomology of T. So it's a functorial way of assigning a cohomology class to any T given a family parameterized by the functor. And that'll be kind of sufficient for this thing to go through. Yeah. Yes, yeah, it should be positive. Yeah. So because you want to take the square root. So yeah. I'm kind of like, yeah. In particular cases, there's like lots of stuff to check. So that's one of the things you want to know that your normalization is kind of positive definite in the sense that any map from BGM, BGM with finite stabilizers, the pullback is a non-zero thing.
Is there anything about, like, can you say anything about the structure of something that you are considering, like maps from A1?
Oh yeah, great. Okay. That's good. That's a good segue.
The reason that I'm asking, apparently people in case stability do something along these lines.
Yeah, oh yeah, so this is an example. So I've erased now the examples, but one of the examples is that, so a map from A1 mod GM into the stack of polarized varieties is a test configuration in the language of K-stability. In fact, you can formulate K-stability in this framework. There's a, I saw in a paper of Donaldson, he studies this thing called the normalized Futaki invariant, which is actually, you can phrase that as a class, and there's a class in H2 and H4 on that moduli stack. And so this would be an example of that question, which I think is wide open, and it's really kind of a puzzle. Yeah. Yeah. So, okay, but so about the structure. Yeah. So let me just talk. So the idea is then once you could find, if you could give a positive answer, there's kind of a lot to do here. There are some results along the lines, but I'm just going to kind of cut them out because I want to get to some of the interesting stuff. So. But the point is that once you have this existence and uniqueness question, so for an unstable point, does there exist a unique map from A1 mod GM which maximizes it? Then you can ask, do you get an actual nice algebraic stratification of your moduli problem based on the class of this map from A1 mod GM that maximizes it, say, based on the actual value of the maximizing A1 mod GM, for instance. So in the case of vector bundles on a curve, you get this. And so there are some kind of results that certain properties of the moduli stack that you're considering, which will make that all work once you solve this existence and uniqueness problem. But
can you somehow also define polystable in this way, or?
I don't know. Yeah, I mean, yeah. Yeah, I don't really know. Yeah. Okay. All right. So. But let me talk a little bit about the structure of this question, because that's actually the title of the talk. That's kind of what I will. So this is all well and good, but it's not a very So let's look at the structure of this problem. So the problem is that the problem is that maps from A1 mod GM. Sorry, I'm struggling with how to express this in a good way. So right now, I've just given you a point in a moduli problem, and there's some giant infinite set of all maps from A1 mod GM, and I've given you a number on all the points in that set, and I'm asking you to see if there's a unique maximum. And that's like a just totally random problem. So finding a maximum of some infinite set is not a problem that you can solve readily. But one thing that is a problem that you can solve is if I give you some topological space and a continuous function on it, and ask if you can find a maximum, then there's some hope that you can actually solve that problem, because there are all these kind of normal ways that you might do that. So that's the goal. So the structure of the problem is to realize. So Kemp proves it for affine quotients. It's true as well for projective quotients. You can deduce that from the affine case by considering the affine cone over projective variety, and with an appropriate linearization. But yeah, so Kemp proves it for the stacks of the form affine modulo G. And this is like what I'm about to. No. It's hopeless. It's not always true it depends on the classes that you write down. But the idea is, what I'm trying to do is actually, what I think I can do is find a really good criterion that you should put on the stack itself that makes this problem manageable. So the realized maps. So the goal would be to realize the maps from A1 mod GM to F to X, along with an isomorphism. To realize these things as points in some topological space. What?
I mean, the topological space should be some sort of finite dimensional.
Oh well, okay. That turns out to be too much to ask, but okay. So the basic issue is that maps from A1 mod GM to an algebraic stack tend not to actually come in large algebraic families. So in other words, an example of this would be, let's consider A2 modulo GM squared. So this is kind of a toric thing. It's described by a fan like this. And now actually for any rational point in the cone here, so for any rational point in the cone, so gives you a map from A1 mod GM, a toric map from A1 mod GM into A2. That's kind of isolated in moduli. And now furthermore, if I'm only interested, let's say I'm only interested in such maps up to ramified cover, because I actually forgot to mention, but in all of these uniqueness statements, you can only, this is still only a unique maximizer up to the operation of raising the one parameter subgroup to a positive power. So you can never actually get quite the uniqueness. You always have uniqueness up to this kind of ramified coverings of A1 mod GM by the map z goes to z to the n.
And I mean, actually then you have also the parabolic.
You have that will come out of this, but in fact there's a parabolic, and a one parameter subgroup that defines it. Yeah, that's canonical. So if you're only interested in parameterizing maps like this up to these ramified coverings, then any kind of rational ray defines such a map up to ramified coverings, and so I can think of A2 mod GM as having somehow a one simplex. So the maps from A1 mod GM to A2 mod GM squared are kind of naturally up to ramified covering are naturally the rational points of a standard one simplex. So I should consider that to be a family of maps from A1 mod GM into A2 mod GM squared, a family parameterized by this rational one simplex. So this is kind of an example, but there's, So in general, what you should do is the following. You should say, consider maps. So I can construct this object, which is kind of a combinatorial object, the degeneration space. So given my moduli problem and my point, this should be this set of maps from an mod GM to the n to x along with an isomorphism with my given point, and there should be some finite kernel and stabilizers. And then what I should just do is form a space, which is just the formal colimit of all these things. So we see that for A2 mod GM, I want to say A2 mod GM squared. I want to say that the space parameterizing maps from A1 mod GM up to ramified covers is just a standard one simplex. And similarly for an mod GM to the n, the space of maps from A1 mod GM into that thing is going to be a standard n-1 simplex. And so this is like a reasonable thing you can do. You could kind of consider the formal union of it. So to each map like this, you just assign a standard n-1 simplex, and then you just take the formal union. And I haven't really said what the colimit is, what the maps are in this colimit, but to any matrix with non-negative integer coefficients, I get a toric map from a to the k to a to the n, and I can restrict along such things. And those are the gluing maps that I want in this formal thing. This formal space. So this would be called the degeneration space. And this would be a totally strange thing to do if it wasn't for the fact that people were already doing it. So the example is if G is a simple group, then BG has a single point. And the degeneration space of BG is actually just kind of homeomorphic to what's called the spherical building of G. So which is kind of a combinatorial object that is very close and remembers a lot of the structure actually of the simple group that you started with. But another example is if you were to take, if X were a toric variety and you look at this space associated to this toric variety and its generic point, then this thing is actually homeomorphic to the support of the fan. So if you have a normal toric variety and you take a generic point in there and you form this construction, then this formal colimit is actually homeomorphic to the support of the fan minus the origin modulo the scaling action. It's not quite a simplicial space. It's like a simplicial space. So you have a set for every n, and then you glue these things together. So it's like the geometric realization, except that there are more maps. So for instance, if you have a 1 simplex, you formally have a 1 simplex, but for any rational point in that 1 simplex, I have a 0 simplex. And if I have if I were to have a 2 simplex like this, then for any kind of rational line in there, I would have a 1 simplex. And so it's like a semi-simplicial set, but except that there's more maps that you're gluing along. But in examples, it turns out that these things are actually just homeomorphic to realizations of semi-simplicial sets. So that's in both of these cases, yeah. So this function mu actually gives you a continuous. So the function mu, which we define for a map from A1 mod GM as f star of L divided by the square root of f star b, actually extends to a continuous function. And so the interesting thing about this space, so when x is of the form V mod G, so an affine scheme modulo reductive group action, then this topological space has a very special property. So then any two rational points are connected by a unique rational 1 simplex. So you can think of, the thing that makes Kemp's argument work, like the essential observation that Kemp had, which is that if your thing happens to be of the form V modulo G, I mean, this is my reinterpretation of it, but if your thing happened to be of the form affine modulo reductive group, and you form this large topological space, I mean, it's not just a space, it comes equipped with the notion of what are kind of simplices inside that space. And any 2 points are connected by a unique rational 1 simplex. And if you look at the way this function is constructed, if you restrict it to any rational simplex, it'll be kind of strictly convex, just by its construction. So if you have this kind of convex space, and if you have a convex function on this convex space, as long as it's bounded, it will have a unique maximum. As long as it's kind of bounded in a suitable sense, it'll have a unique maximum. So that's the argument that's the structure that Kemp's argument takes. And in fact, there's a large class so that's a property of V mod G itself. This property that any 2 points in the degeneration space is convex. So there's a large class of stacks. So which I've been calling weakly reductive. Such that the degeneration space is convex in this way. So, the example would be if you take if you take a families of objects in dB in the heart of a T structure on the derived category of X. So this would be this would be an example of these stacks where, so if you just take coherent sheaves, something like that. So, the normal way of thinking about coherent sheaves is this stack is by locally taking it as a quotient of a quote scheme. But for that, in those cases, the global quotient of the quote scheme by some reductive group won't actually be weakly reductive in this sense. But if you actually take the entire stack of all coherent sheaves, this stack has this very strong symmetry, which says that the space of degenerations of an unstable point is kind of convex. And so this is the kind of stack that you should be looking for when you're kind of studying instability, because for these things the uniqueness is essentially automatic. You just need to prove boundedness. No. This property of being weakly reductive is essential to the stack itself. Oh, this is the end of the talk, by the way. I haven't given a definition. Yeah, there's a definition. So it turns out that kind of like by a theorem of myself and Anatoly Pregel, that this mapping stack actually is algebraic. So it turns out that not only can you talk about points in this thing, but this actually has the structure locally of an algebraic stack. And oh, sorry, yeah. Yeah, it's locally finite type algebraic stack. So when this is a quotient stack, this will be some giant disjoint union over all conjugacy classes of one parameter subgroup in the group G, and then for each of those things, it'll be all the BB strata associated to that one parameter subgroup. So this thing will be enormous, but it'll still be algebraic. And you have an evaluation map like this. So I can take a map from A1 mod GM and restrict it to the point 1, and this gives me now an evaluation map to X. And the property of being weakly reductive should say that this thing satisfies the valuative criteria of properness. This evaluation map. So in the case of this example, this is saying the quote schemes are proper. So it's the properness of the quote schemes is what guarantees the uniqueness. But this is the definition of weakly reductive. Well, in the case of X mod G, it's kind of special. So if X mod G and X is affine, so if it's affine modular reductive, this criterion is satisfied. But for instance, this criterion is not satisfied if you're projective modular reductive. So kind of from the perspective, that's why Kemp was able to prove this first for affine things, and then later you can deduce it for projective things via a trick. The natural place to study this problem is an affine modulo G, because that's the stack that's weakly reductive. Yeah. Oh no, I was done. I was done like a few minutes ago. Thank you.